Okay, welcome and thank you for joining us today. It's my pleasure to introduce Delphine, who I'm guessing most of us already know, but I will give you a brief bio on Delphine's travels to get to this place. She received her BSc Bachelor of Science in Chemistry from McGill University, and then a Master's in Environmental Science, Policy, and Management from UC Berkeley, followed by a PhD in Chemistry, also from UC Berkeley. She then worked here in Boulder at CU Boulder on a NOAA Climate and Global Change postdoc fellowship, and she's currently an assistant professor at the chemistry department at CSU. And some of you also might have seen her roaming the third floor over the last few years, where she has been a long-term visitor in ACD. So today, Delphine's going to present her work from her research group on organic acids and the switchable reagent SIMs. Okay?
Great. Thank you. And thank you all of you for coming. I know it's an absolutely beautiful day. Oh, what am I supposed to do? Oh, yep. Okay, so thank you all for coming. So as Becky mentioned, I do, my dirty little secret that I try not to tell too many people is that I spend some time in an office across the hall from Jim Smith, so I'm there about one to 2 days a week, which is fantastic. So I decided to take the opportunity and take up Becky on her offer of giving a seminar here so that I can perhaps tell you a little bit about what my group is doing so that we can hopefully start some discussions about some of the interesting instrument development and some of the interesting science and some of the conundrums that we're just beginning to come across. So as Becky mentioned, I'm going to be talking about atmospheric oxidation chemistry, and in particular, the work my group has been doing in trying to use multiple reagent ions to do chemical ionization mass spectrometry. And I will explain to you what that means. I know there are a few modelers in the room. Thank you for coming. But to frame this, this is a photograph from the SOAS ground site. Several of the people in the room were participating in the project, so you know all about it, so I'm not going to give you lots of details, other than to say that what this picture illustrates is the problem we have in atmospheric chemistry. We have very complex terrain with lots of plants, and those plants emit huge amounts of volatile organic compounds, which of course get oxidized in the atmosphere. And the real questions we have are fundamentally about how changes in the chemical properties of the atmosphere affect the optical properties, so climate, and the quality of the air we breathe. And the question really is how do these organic molecules that are emitted by plants, how does their chemistry change the properties of the atmosphere? So we want to understand oxidation chemistry. So my very quick little cartoon to illustrate exactly what my group is after is this. So as you all know, hydrocarbons, so volatile organic compounds, are emitted by plants into the atmosphere, oxidized in a photochemical cascade, and either they're lost by deposition along the way, or they end up as aerosols, or perhaps some of that carbon ends up as CO and CO2. So obviously, all of the molecules in the photochemical cascade, the aerosols, and then of course the end oxidation products have different impacts on air pollution and climate. If we add in anthropogenic species, the process is really to add some complexity to the chemistry. Sometimes we speed up these reactions. Sometimes we just change the identity and the characteristics of the aerosol. But the problem is in all of these arrows, and it's in all of this chemistry. So we know that there are huge numbers of different types of compounds. There are organic nitrates, organic sulfates, peroxides, epoxides. You go to an organic chemistry textbook and you pull out the functional groups and you see that they're pretty much all listed. And all of those are present in the atmosphere. And they all do interesting chemistry. But they pose an interesting problem. There are two questions here. Really, the first one is how much of this chemistry do we actually need to know in order to predict air pollution and climate-relevant processes? As all the measurements people in this room are fully aware, it is quite challenging to measure all of these molecules in the atmosphere. So I think it's worth considering how many of them we actually need to measure. And I don't think we know that yet. So we're currently in the stage where we're trying to measure everything and trying to figure out what it means. So if we're in that stage, how on earth do we measure them? So how do we measure them in the gas phase and in the particle phase? And again, this huge number of functional groups. So I did my postdoc with Jose Jimenez, and he used to love this figure. So I thought I would use it here. So this is a figure that was published in a paper in ACP a few years ago, and the idea here is that if we think about measurements, we can think about these really on two axes. We can think about chemical resolution. So do we do functional group analysis and say how many alcohol groups there are, carboxylic acid groups there are? Or do we think about molecular identification? Do we think about whether it's, say, hydroxybutyric acid or isocrotonic acid, how much molecular identification we have? So that's kind of this conceptual axis along the bottom. But of course, that doesn't really help if we only measure 0.1% of the molecules in the atmosphere. There is a question of completeness. Now, this figure was really designed for thinking about aerosol chemistry, and it was obviously, it's a few years ago, and we've had some shifts in the framework in which we think about aerosols. So they used to like to point out, if you can only measure one class of molecules, so one small amount with no differentiation or chemical information, and you measure only a small fraction of what material there is, then that is a pretty useless instrument. What you want is an instrument that can give you molecular identification of absolutely everything, right? And so you could put various instruments that are used in different places along this plot. And I think they've shifted in the last few years. There have been some pretty impressive instrument developments that have changed how well certain instruments work. But I think the real shift in our framework of thinking about measurements over the last few years has been the addition of different axes. And so we're not only after chemical resolution, and we're not only after completeness. I think we are now after volatility information, potentially polarity or oxidation state information. And the challenge here is that we want to measure these different axes, and we want to understand the material well enough that we can gain some chemical insight onto the system, and then perhaps even go and take it and put it into a model and really see if we can change our understanding of atmospheric chemistry. So this is perhaps what we want. But what I've realized in looking at this is that all of these figures only focus on aerosol measurement. And of course, if we go back to this picture here, a lot of the chemistry is occurring in the gas phase. And I think that we're beginning to realize that we need to start adding in not only aerosol phase in terms of chemical resolution and completeness, but we also need to think about including this in the gas phase. So that's what my research group is really going after. We're trying to understand how, what we would love would be an instrument that would give us complete chemical resolution, one that would give us all of the molecules in the atmosphere, and one that would do it on give us information about volatility and polarity and oxidation state. Now, I wouldn't want to think about analyzing the data from that instrument, but of course that's what we're really after. The problem is that the gas phase chemistry really affects organic aerosol formation, and there have been some really interesting insights in the literature in the last few years. If you take something relatively simple, some nice little monoterpene, and you oxidize it with ozone, it turns out that not only do you make a great many molecules, different types of molecules that of course all go on to do different types of chemistry. These molecules can do something called auto-oxidation, and they make something that is currently being referred to as LVOX, so extremely low volatility organic compounds. And so we have this combination, and we have these hugely complicated gas-based chemistry schemes. And I think from a measurements and analytical chemistry perspective, trying to figure out how we can measure all of these intermediates, and some of them have very short lifetimes, so perhaps we don't measure some of these, but how do we measure compounds that have varying oxidation states, varying sizes, molecular weights, and such? And there have been some approaches, two-dimensional chromatography provides a lot of insight and a lot of information. Classically, a lot of atmospheric chemistry has been done with spectroscopy techniques, but those are actually quite limited in terms of being able to quantify and identify large numbers of very different molecules. So what we're really trying to do is think about something that we're calling multi-reagent chemical ionization mass spectrometry, or switchable reagent ion mass spectrometry, one where we can take advantage of mass spec's ability to measure large numbers and over large of molecules at effectively the same time, and one that allows us to control what type of chemistry we measure. So what I'm going to do, actually, with this talk is, just so you know, is I'm going to talk a bit about our instrument, about multi-reagent chemical ionization mass spectrometry, about its limitations, and I think the limitations that we're learning apply to many other measurements that are out there. Then I'm going to talk a little bit about how we can take the vast amount of data that we are collecting and actually perhaps learn something from it. So some qualitative bulk analysis, and I'm going to use some chamber experiments that we did at CalTech in January as the example. And then we're going to talk about quantitative analysis. So how do we figure out exactly how many parts per billion you get in the atmosphere of some given compound, and we'll talk about the limitations of doing that with SIMS. And then finally, I'm going to use that quantitative analysis and show you a little bit about some of the science we're thinking about in terms of formic acid, which is one of the more interesting oxidation products. So in terms of our measurements, we have something, the switchable reagent ion. We went for the longest acronym we could find. So switchable reagent ion, high resolution, time of flight, chemical ionization mass spectrometry. That's the name of this instrument, or the type of instrument, effectively. So what we do is we pull air in. So this is a real-time measurement. We pull air in to an ion, what we call an ion molecule reactor. And molecules in the air then have the opportunity to react with whatever other ions we give it. So we can produce currently I- ions, so iodide, or we can produce acetate ions. And either one of those, depending on what we feed the system, can react with some given analyte, so some molecule in the atmosphere. We're just going to call this HA and pretend it's an acid. And we can do a few different types of chemistry. So we can potentially form adducts. So with iodine and any molecule, turns out peroxides, carboxylic acids, they form adducts with iodine. So you now have a negatively charged ion. So what we've done is we've taken our analyte and we have charged it. We can also do a proton transfer reaction. So we can take the proton from our molecule of interest and move that proton over to I-. And now we have, since we've removed a proton from our molecule of interest, we now have an anion. And we can do a similar set of reactions with acetate. So now that we have charged the molecules in the atmosphere with whatever chemistry we choose to use, those molecules can then, those ions rather, can now get sent through a series of quadrupoles. The quadrupoles are really there to direct the ions into our mass spectrometer. And then we use a time of flight mass spec to actually analyze the data. So there are a couple of important points here. So the first important point is that we have two different reagent ion setups, and we can actually switch them very rapidly. We typically operate by switching it for about 5 minutes on I- and 5 minutes on acetate, but we can really run this as fast as we want, although probably no faster than 10 to 30 seconds at our current setup due to pressure fluctuations. But we prefer having a little bit of averaging time. So we're looking at a few minutes in each of these different reagent ions. The reason we would go to different reagent ions is that we classically think that these different reagent ions allow us to access different types of molecules. So acetate is classically, this isn't entirely true, but it is classically considered to measure carboxylic acids. So using acetate ionization allows us to access and measure carboxylic acids in the atmosphere. Iodide, a little more general. Some carboxylic acids, but it's also been demonstrated to do beautiful measurements of various peroxides and other types, and nitrates and other molecules. So So we have these two different reagent ion systems. We can switch them relatively rapidly. We can measure this in high resolution. And high resolution is useful because unlike a straight quadrupole, it gives us two key advantages. The first advantage is that we have high resolution data, so we can identify how many carbons, hydrogens, oxygens, nitrogens, et cetera, are in a given molecule. So we can do elemental composition and hopefully actually start to determine molecular identity, or at least oxidation state, No to C and H to C ratios, and that sort of thing. But the other aspect of a time-of-flight mass spectrometer is that it's really, really fast. And what that means is that we can get full mass spectra. So from molecules that are 12 Daltons up to several hundred on the 10 Hertz time scale. So of course the goal is that we'll end up doing eddy covariance flux measurements. But before we do that, we need to understand how this instrument works. And that's really turned out to be a non-trivial problem because we get a vast amount of data. We get full mass spectra with high resolution, so we can, again, figure out the different elemental compositions, and we get that very quickly. So the real challenge here is taking the data and then understanding what it means and what we're measuring. So that is the struggle. So this instrument has gone through a few iterations. In SOAS, it was a bunch of wires, and most of them are hidden behind this computer. But we home-built a set of shelves at SOAS because it was our first project. We'd had the instrument for a little under a year at that point. Then at CalTech, it underwent a few changes and acquired more tubing and wires. And then more recently in our lab, we've got the system fully racked, and it's looking much more field deployable. And we'll be using it this summer at Frappe. So these switchable reagent ions, what do we see? So here's your standard mass spectrum for acetate ionization and iodide ionization. And there are a lot of things that you should be able to see here. The first is that the gray is our background. If we add ultra high purity, zero air to our instrument, so we should be adding nothing into the inlet, this is the mass spectrum we see. So we see a lot of ions in the background mass spectrum. So if you are looking at someone's data who has a mass spectrometer, a time-of-flight mass spectrometer, the first question you should be asking is, what is your background? And have you background subtracted before you try to interpret your data? And it is amazing to me the number of people who attempt to who forget in the field to look at the background. And my graduate student and I were guilty of this for a few days and being completely fascinated by all these peaks that appeared at about 600 Thomson units until we realized that they were all background. So the gray is the background, so watch the background. But then you still see the red, which is the actual measurement in this case. And you still see a huge number of peaks. So there are a lot of molecules in the atmosphere. That's what we get out of these figures. Lots and lots of different molecules. Some of them, so here again in I-, we still see above background some of these really high molecular weight compounds, but we're not entirely, we don't really think they're real because their background does shift a little bit. So background is a really big issue in these measurements. So what we're measuring from acetate, it turns out we're measuring organic and inorganic acids. This isn't a surprise, published in the literature by quite a few other groups. We also measure some epoxides and hydroperoxides. We know we measure them, as I'll show you in a few minutes. It's a little difficult to tell exactly what you're measuring, though, in terms of isomers. With I-, as I mentioned, we measure lots of different functional groups. All right, so we have these switching reagents. We can operate them. In this case, we were operating on the tens of 5-minute time scales, and you can see we can measure iodide for several minutes. We switch and we measure with acetate ionization back to iodide. It turns out, for the instrumentalists in the room, there are some tens of seconds now. We've pulled this down, but we do have a changeover time, and that is entirely due to pressure differential, because it turns out no matter how you attempt to control your pressures, in the ion molecule reaction region, where we're looking at a few hundred millibar, tiny fluctuations really change your chemistry, and it takes a few moments for the pressure to normalize. So that's our limiter in terms of how fast we can switch, is really how long it takes for our system to have the pressure flatten out. So we have these two types of reagent ions. So there are a lot of questions as to why you would bother with multiple reagent ions and what information this gives you. So my students and I, and then a few other groups, we've been talking a little bit recently about different types of reagent ions in chemical ionization mass spectrometry and what they could possibly mean. And about a couple of months ago, this is the figure that we were discussing. So if you think about molecules in the atmosphere, you have things that are reduced, stuff like methane, and then you have stuff that's really, really oxidized, these extremely low volatility organic compounds that are created by this auto-oxidation process. So things with O to C ratios over 4, over 5, very, very highly oxidized molecules. Okay, so the idea was that things like proton transfer reaction mass spectrometry, water cluster mass spectrometry should be getting at things that are slightly more reduced. And then we thought, well, maybe things like nitrate SIMs are only getting at the things that are the molecules that are really, really oxidized, very, very high O to C ratios. And then you have these reagent ions like acetate and I- that we use, and then CF3O- that the CalTech, that the Wember group uses. And these seem to access molecules that are sort of intermediate. We can't access the extremely low volatility organic compounds, but we also don't access pure hydrocarbons. So we're sitting somewhere in the middle. So this was the picture that we had. And what I'm going to do in the next few moments is use a bulk analysis approach from various chamber experiments where we took a whole pile of mass spectrometers and put them all in one room, one very hot and stuffy room, attached them to a chamber and looked at the data. And what I'm going to do is use this data to see if we can refine this picture of chemical ionization mass spectrometry a little bit. So I'm not going to go through the details here. You're all atmospheric chemists in the room. This is the CalTech environmental chamber. This is the month of January. I went on vacation, and my poor graduate students went to CalTech for the month. They did 30 experiments in about 31 days. It took about 10 hours per experiment. There were a large number of groups measuring almost entirely gas phase species. Right, so we had the gas phase component of the atmosphere as well covered as I think our community currently has the ability to. The aerosol phase was only covered by an aerosol mass spectrometer. So that was poorly understood. So what I'm going to do is show you a few mass defect plots. So for those of you who do not do mass spectrometry in the room, I will give you a primer. So the idea here is that along the x-axis, we have mass to charge ratio. We assume that the charge in everything is 1. You can think of this x-axis as basically being molecular mass. And then we have our mass defect on the y-axis. And what a mass defect is if you think about your isotopes, carbon has a nominal mass of 12. The most common isotope of carbon has exactly, we've just determined as chemists that we were going to call it 12.000, so it has a mass defect of 0. A single oxygen 16 isotope, which is the most common form of oxygen, has a mass of 15.994 AMU, so it has a slight negative mass defect. Hydrogen, a slight positive mass defect. So if you take your molecule of choice here, so C10H16O4, you add up all the carbons, the hydrogens, the oxygens, you figure out that it has some molecular weight. So in this case, the molecular weight is about 200.1. So, and you can tell that it has a mass defect, being the difference between the molecular weight and the nominal mass of 0.1. So it would lie, so this molecule would lie on the mass defect plot right about as a dot right here. So on the mass defect plots I'm about to show you, every single ion that we measure in the mass spectrometer is a single dot. And they have all been calculated this way. So if we take an experiment where we took alpha pinene, we reacted it with OH radicals, and we look at the gas phase composition a couple hours into the experiment, this is what we see in mass defect space. So we see along mass charge ratio on the x-axis, mass defect on the y, you see the spread of lots of dots. So the lots of dots means lots of ions. So again, the groundbreaking idea that we have lots of molecules in the atmosphere when we do an oxidation experiment. But we can get a little more information out of this. We're seeing mostly carboxylic acids, but not every ion we see is a carboxylic acid. We see a large range of molecular weights, and as a chemist, I was initially surprised that we could possibly see things that have a molecular weight of 300 Daltons sitting in the gas phase. I think that's quite impressive. But we do see this pretty large diversity of molecules. Okay. There was one caveat, and that is that we were concerned with acetate ionization, that acetate reagent ions would just cluster with whatever molecules we were looking at, and this might be what's giving us these really high molecular weight species. So we were concerned about it, and it's something that I think everyone who does SIMS should continue to be concerned about. But what I've done here is taken our iodide measurements of the exact same time period, or a couple minutes later, but the same time period in the chamber experiment, and overlaid those as our red dots. And actually, the acetate is in front, and then we have I- reagent ions behind it, and then we have nitrate SIMS data in green behind that. And the nitrate SIMS data came from Jordan Kirschmer and the Aerodyne crew who were out at CalTech with a nitrate SIMS instrument. And again, there are several things you should notice from this. First off, all of these instruments see these really high molecular weight compounds. Some instruments, namely nitrate SIMS, sees higher molecular weight species. So this tells us that nitrate is accessing a different type of molecule. But we also see that acetate and I-, they see different molecules. And what's interesting is that there isn't a very good pattern as to which molecules each system sees. So with acetate, we can see acrylic acid and methacrylic acid. With I-, we can only see acrylic acid. We can't see methacrylic acid, and we have no idea why. But there are dots that we see with one type of reagent ion that we don't see with the other. So we verified that these high molecular weight species seem to actually be there. We have some overlap with reagent ions, which is great for intercomparison purposes. Our instruments, acetate ionization formic acid, intercompares beautifully with our I-, which is reassuring. But there's this question as to how oxidized and how all of these different molecules, what they see. So the blue is the acetate, and if we go back a moment, you will recall that oxygen has a slight negative mass defect and hydrogen a slight positive one. So things that are higher in this mass defect place should be slightly more should be slightly less oxidized, and things that are down and are further down in this figure should be slightly more oxidized. So if we take that and we go and we look at this figure here, what you see is that we have some things that are slightly more oxidized. So one could perhaps say that nitrate measures things that are slightly more oxidized than acetate and I-, and maybe acetate sees things that are slightly less oxidized. Yes, question.
You might get to this later, but I was wondering if you were assuming that each one is the molecular ion and you're not accounting for fragmentation.
Yeah, no, so that's a really good question. So the question is whether or not each of the dots on this figure, each ion, if we're assuming that it is a molecular ion, so the original molecule that was in the atmosphere, or if it was something that broke apart in the mass spectrometer. And the answer to that is that initially we assumed that everything was a molecular ion, and we are now realizing that that is not the case. We do have some fragmentation products, but not much. And we use standards of large molecules and put them into our system and see how much fragmentation we get. We get very little fragmentation. But what we do get is with acetate, we get some of our molecules combining with acetate ions. And so instead of being over here, that molecule is now over here on that figure. So some of these dots can be a little misleading, and I think that's a really, really important point to take home from these bulk measurements, is to be very careful with interpreting every single dot as a single molecule in the atmosphere, because some molecules get double counted. Yes?
Have you basically decided that those are all carbon, hydrogen, and oxygen?
They are not all. For the purposes of this figure, I believe we eliminated all the heteroatoms. So, oh, no, that's not true. We actually included them, but this was a low NOx experiment, so there was almost no heteroatoms in here. So no nitrogen and sulfur in this figure. But in the next plot, I have the data from the exact same experiment. So alpha pinene plus OH, but in this case, we added NOx. Turns out there was some NOx in this experiment too, but not too much to be worried about. So here what you see is this is where we're trying and get some insight onto chemistry. You can see that when you add something like nitrogen, you of course change the chemistry of the system. So these two plots look a little bit different, and you make the system a little more complex. But interpreting any science from this type of figure beyond that is a little tricky, and I'll explain why in a moment. But if we look at these figures and we go back to our image of how these different ionization techniques work along our axis of reduced to oxidized, or perhaps it's oxidation state or O to C or polarizability, nobody seems to really know. But if you choose your axis and you think about these different types of reagent ions. So PTR does an amazing job measuring hydrocarbons, and it measures quite a few of the lower oxidation state, but slightly oxidized molecules. Acetate seems to cover a fair amount. I- is perhaps slightly more oxidized molecules than acetate, and then nitrate is quite an impressive reagent ion. It seems to measure quite a large variety of molecules. However, I will point out that not all of these, at least these two reagent ions that we're studying, I don't believe measure a continuum of any individual molecule. They're more like a punctuated continuum of oxidation that we measure. And my point with this idea is, or with this figure, is that all of these reagent ions allow us to access different types of molecules. I did not add any punctuation on the nitrate or the PTR because those are not my measurements, and I'm not entirely comfortable with those systems, but it wouldn't surprise me if we shouldn't think of them as measuring everything. But I think the point here is that if we actually want to measure all the molecules in the atmosphere, or even some suite of oxidation state, and try and understand the chemistry, then we can't just use a single reagent ion. We need to have multiple reagent ions in order to understand all the molecules out there. Okay, so that's our bulk analysis. But there's a big question. This is qualitative. I attached no concentration numbers to that data, nor will I, for reasons that I will explain momentarily. We have a problem with chemical ionization mass spectrometry, and that is that it is very difficult to quantify what we are measuring. We measure a large number of molecules. Can we identify and calibrate them? If I ask the question of can we identify and calibrate them all, the answer is definitely not. Can we identify and calibrate a few of them? Yes, but it isn't trivial. So at SOAS last summer, I think you are all familiar with this experiment. We were in Alabama. We were at the ground site with our chemical ionization mass spectrometer. And I'm not going to go through this figure because it's very detailed, but what we did is we went to a lot of effort to attempt to design an inlet system that would exclude particles, and I think we did a very good job of that. We also created an inlet system that would allow us to, with a paranoia that was perhaps justified from my postdoctoral group, we were so concerned about being able to quantify, we went to huge efforts to attempt to figure out how to quantify our measurement with multiple techniques. So this is what the setup looked like, perhaps a little excessive. This was our calibration system. Most of it was designed ahead of time, but assembled in the field. This was our inlet, and so what you can see, the key things about our inlet is that we have a huge bypass. So we pulled air through our inlet really, really quickly to minimize any loss. So we pulled air quickly to minimize loss. We sampled in air from a different line so that we would exclude particles. And then we had a separate inlet, actually we had two of them, so we could add zero air, so we could do background measurements very frequently, and that we could do calibrations very frequently. And by very frequently, I mean once an hour, which for some gas phase measurements is quite common. I think for mass spectrometry it's a little less common. But we did very, very frequent calibrations in zeros. We did the calibrations in two ways. So every hour, this is what we would do. We would run zero air for about a minute, so we would get a very nice stable background. We would then add an amount of formic acid in zero air. So we would effectively do an external standards calibration for the analytical chemists in the room. So we would add formic acid in zero air, and then we would add a high amount of formic acid in zero air. So we would start out with about 2 parts per billion of formic, and then we would add in about 15 parts per billion of formic acid. We then turned off the zero air, and we pulled in atmospheric air. And so what we then did was effectively a standard addition. And so we would add in formic acid on top of that which is existing in the atmosphere at the time, and we would use these two different measurements. So of course, in that case, if there's some formic acid, in this case, you can see about 3 parts per billion of formic acid in the cartoon. We would add our 2 parts per billion to the free, and we would see slightly elevated amounts. So this gave us two separate measurements of how sensitive our instrument was to formic acid. It turns out, the bottom line, I'm not going to go through the excessive amount of data we collected. It turns out that these really frequent calibrations were not actually my assistant professor paranoia. They were actually required. So it turns out that in particular, the background of the instrument, which is in black here, is a function of time for the entire time we were measuring its SOAS. You can see that the black trace along the bottom of this figure actually moves. And it moves by a non-trivial amount. This is normalized counts per second. That wiggle is important. It's the background we're subtracting, and that changes. And the mass spectrum of it changes a little bit too. So this is our background. It changed. And then we had this low amount of formic acid and a high amount of formic acid, and those guys changed as well. So what this really means is that the sensitivity of the instrument was changing on the time scale of hours, and the background of the instrument was changing on the time scale of hours. So it was very important for us with our instrument to at least do those frequent calibrations. And it's something that I think some instruments seem to be more susceptible to these variations than others. So it's very, very instrument specific. But for our system, at least, we needed to do these very frequent calibrations. Fortunately, if we calibrate the instrument with these external standards and standard additions, we get the same numbers. That's what this figure over here shows. So if we did formic acid from external standards and standard additions, if we use these two calibration techniques, we have a pretty good R-squared value of 0.99. We're looking at no biases. And that's what this says. If you use standard additions and you get the same data, we have no bias in our instrument. Okay, so that's good. So we can calibrate formic acid. And if we're lucky, we can then know a relative ionization efficiency for some other molecules that we have standards of, and we can then calibrate those. However, there is a very important caveat. And that is just because we can calibrate on a molecule in the lab doesn't mean it's the only molecule that we actually see in the field. And the example of this is isoprene epoxide and the isoprene hydroperoxide, so IEPOX and isopoo. And it turns out that these two molecules, which have very different structures and therefore some quite different chemistry. Turns out we measure them with our acetate ionization at exactly the same mass to charge ratio. Same with our I- ionization. And we have a little glimmer of hope that the IEPOX, so this molecule, shows up as not a fragment, but as a non-cluster in some very small amount in the acetate ionization. So we may actually be able to separate these two. But just because we were able to do some beautiful calibrations of IEPOX in the lab, turns out that all our SOAS data is impossible to interpret because we were actually really measuring the sum of these two isomers. So again, this is something to just keep in mind when looking at data. So the question I asked was, we measure lots of species, but can we identify and calibrate them? Well, we need authentic standards in order to do that, which is easy for formic acid and really hard for things like isoprene hydroperoxide. And in the field, I think using standard additions in order to identify interferences is an extremely useful tool. So I've got 3 caveats for you in terms of interpreting SIMS bulk data. First is that quantitation is very challenging. So the relative size of the peaks here is completely meaningless in terms of these mass spectra. So I made my students make each of the dots, or attempt to make each of the dots the same size, because we don't know the relative amount of all of these different ions. Each reagent ion has different ionization efficiencies for different molecules. Okay, each peak is not necessarily a single isomer. Remember, IEPOX and ISOPU, they show up at the same mass-to-charge ratio in our system. And whether or not that's important really depends on your science questions. And then thirdly, some molecules get double counted. So this is John's question. Some of these molecules show up in 2 different places because they're ionized in different ways or fragment in different ways. But to a general extent, we think that's actually relatively minor. Okay, so in the last few minutes, what I'm going to do is show you very briefly some data about formic acid. Because this is quite interesting. So this is the one-time series we have really well calibrated and quantified from SOAS. And I'm not going to go for all of this in detail, but formic acid is an oxidation product. It's an endpoint oxidation product. It's only got 1 carbon in it. So after you oxidize isoprene or a monoterpene a fair amount, you'll start producing some formic acid. Anthropogenic sources, they're biomass burning sources. There's the sinks of it are OH oxidation and then wet and dry deposition. So this seems like a really simple molecule. And the problem is that the models cannot replicate in any way, shape, or form the measurements. And there's been some suggestion in the literature that there is a large biogenic oxidative source of formic acid. So this seemed like a really simple problem for us to go and look at SOAS. So, we have this beautiful data set, again, beautifully calibrated, background subtracted. This is from end of June to mid-July from SOAS. So formic acid, lows were around 0 parts per billion, so that was good. And then our highs were around 10 parts per billion, which is pretty high for formic acid. And there are a few things that we wanted to think about. So as I say, it seemed like a simple problem for us to go after, to look at the sources and the sinks and think about the lifetime. But there's a problem, and you should already be able to see the problem. And that is this last point here. Globally, at least, formic acid has a lifetime, thought to have a lifetime of 3 to 5 days. So the global, not the regional or local lifetime, in this data set is very clearly not 3 to 5 days. That's the first thing you should notice here. So we have these strong diurnal patterns, right? So that indicates something of a much shorter lifetime. So what are our sources in our sinks? So we clearly have 3 different time periods. We have a high photochemistry time period. Then it rained a lot and it was really hot and miserable. Unfortunately, I was not there. My poor graduate students were. And then it got kind of nicer and hotter and still humid but less rainy for the last few days. So we have these 3 time periods. I'm just going to focus in on this first time period just to make life simple. But before I do that, I mentioned there was a model measurement discrepancy. It's been documented by several groups. So I called up Dylan Millay at the University of Minnesota, who's been thinking about formic acid in geoschem. And so he kindly ran his model for our ground site. So what you have in this figure is formic acid. It's a function of it's a time series for SOAS. In black, you have our data, our beautifully calibrated, zeroed, intercompared data of formic acid. Okay, and in red, you have the total formic acid from the geoschem model, right? And you can see some really big problems with this model measurement comparison. The first is that the measurements are huge relative to the model, right? So the model is missing the sources by a large amount. It ends up, we need a source that's about 20 times bigger than that in the model. The other thing you can see is that the structure of the diel cycles in the model are incorrect. They're too broad. We do not see the sharp rise and sharp fall. And to me, that is actually the more interesting problem. So there's a similar discrepancy for the aircraft data, and you can sort of see in green, it's mostly isoprene oxidation as the source for the formic acid. Okay, so let's go back to the data. So we can have diel cycles, so you can see these time cycles. So starting in around 8 or 9 in the morning, we see this rise in formic acid, and then it tails off. Okay, so this tells us that we have a daytime source, we have an afternoon maximum, and then we have some loss through the night from dry deposition. We have no evidence for anthropogenic sources. No correlation with CO or SO2. We're pretty sure this isn't an anthropogenic source of formic acid. What's interesting, though, is that if we correlate formic acid, or when I looked at this, I thought, wow, this looks a lot like something I studied in my PhD thesis, which is nitric acid. And nitric acid has a beautiful diel cycle that matches formic acid. And in no way, shape, or form am I suggesting that there is a functional or chemical reason for nitric acid and formic acid to be similar. What I am suggesting is that they have similar sources and sinks, and that we can use the similarity to just tell us something about the lifetime. So if we do a scatter plot, we get a beautiful R squared. And again, that says these two molecules are moving in the same way. And that tends to suggest that perhaps their sources and sinks are coming from the same places. Looking at the data in a couple of different ways, I'm actually just going to zoom in on a few days here. So in black, you have our formic acid. And in red, you have nitric acid multiplied by 10, just so you can see how similar they are. So they have exactly the same rise and exactly the same fall. There are some differences, which I assume comes from NO2 discrepancies, because in order to make nitric acid, you need both OH and NO2. But I think what this tells us is a couple of things. First, that the lifetime of formic acid is similar to that of nitric acid, so we're looking at something of a lifetime on the order of hours. Then what we can say is that these have similar sources, so some fast OH-initiated chemistry. They have similar sinks. And my initial thought was, does this mean that the dry deposition is occurring at similar rates? Because that doesn't make any sense. Because nitric acid is really soluble and has a really high Henry's law constant. And formic acid has a Henry's law constant that's about an order of magnitude lower. So we would expect the dry deposition to be much faster for nitric acid. So there was a problem here. So if we look at this problem and we think about the sink, so what's causing this really rapid fall? If I make a steady state approximation for the production to be equal to the loss of formic acid, I estimate, very back of the envelope, hand wavy estimate, that the deposition velocity would have to be about 30 centimeters per second. And that's about 2 orders of magnitude too high to make any sense. Dry deposition is an inadequate sink for formic acid based on its Henry's law constant. So we need some other sinks. And I've scratched my head about this quite a lot. And the only thing I've come up with is that we have to have some aerosol uptake. So the formic acid has to be going into the aerosols, and it has to be doing that very, very rapidly. If anyone has any other ideas for a very rapid sink of formic acid, I am all ears. So please come and talk to me about it. A couple of interesting notes. This formic acid, nitric acid similarity holds for other sites. So in Bakersfield in California, Jen Murphy's group made some measurements that allowed them to get at the correlation plot we had, and it was very similar. But not everywhere. So wintertime in London, some data was published recently that showed there is no correlation between formic acid and nitric acid. So we have a problem here. So it's clearly something biogenic. So I'm running out of time, so I'm going to skip a few slides and get to the punchline. And that is, we know there's a secondary source We know that solar radiance doesn't really match our formic acid, but temperature does. So we have a strong relationship with temperature. We can fit this to a curve which looks a lot like biogenic emission, but the constants that control it don't quite work out. The time series suggests that, here we go, the first time period has one temperature correlation. The last time period has a slightly different temperature dependence. And I'm not entirely sure how to interpret that as to whether there are different biogenic precursors or if this is all just in the noise of the data. So the sources are some sort of biogenic hydrocarbon. And so what this requires in order to make this formic acid really rapidly is a very fast rate constant and or a very large precursor concentration. So I need something to be what, in my perspective, is kind of unreasonable from a chemistry and kinetics perspective, but we need some massive source. It doesn't appear to be heterogeneous sources. There is no correlation with with any form of aerosol. There is an incredibly weak correlation with the low volatility oxidized organic aerosol. And there's no indication with time series or correlations that this is heterogeneous. The last note of science before I throw out my conclusions is that other acids that we measure have some similarities. They are not identical profiles, so some of these acids, I know this figure is kind of hard to read, but we have different acids in different colors, and some of them look almost identical, like the May or levo ketobutyric acid. Those two isomers overlap. This C4H, sorry, that's really hard to read, C4H5O3 molecule looks really similar to formic acid, but some other ones like the hydroxybutyric acids in orange, they look a little bit different. So, but we still need some sources and some rapid sinks for these other molecules. So with that, I'm going to thank you for your time in listening to me. I'll go to my acknowledgments and then I'll go back to the conclusion slide. I just have to acknowledge Dylan Millay at Minnesota for running all of the model simulations, and then numerous people for helping us with data. And in particular, these two graduate students of mine, Trey and Pat, did really all of the work that I'm just getting to stand up here and talk about it. So I'll leave my conclusions up, and thank you for your time.
Okay, thanks so much. Does anyone have any more questions?
How do you generate your zero air?
We buy it. We buy the ultra-high purity zero air. If we generate the zero air, we have a very hard time making it cleaner than that, and we have a hard time keeping the pressure constant if we have a real-time zero air generator.
I'm going to make you wait for this.
Did the geochem simulations have direct biogenic emissions of formic acid?
So I'm not entirely sure. My answer to that is that Dylan put in every formic acid source that he could find in the literature. And everything other than isoprene oxidation was negligible. So we could add, if we added in a direct emission of formic acid, it would have to be huge. So it's possible.
Yeah, there's Alex's paper lists an estimate for it. I'm not sure it counts as huge, but it's 3.5 teragrams per year.
Right. So I think I'll have to double check with Dylan on that.
Then that might, well, I don't know, might explain the time series as well, if that's.
Well, it would explain, if you can come up with another source, I'll go back to this slide. If you can come up with another source, you can make, you can form the formic acid. If you can have a direct emission, and I can certainly go and do the back of the envelope direct emission that's required, but I know it will be very, very large. If we have a direct emission, we would get that rise, but we would still need the fall every day in the afternoon to work too. So we still need a sink, but yes, I'll check in and see how much formic acid would have to be emitted to make that up. It's a good question.
You mentioned very quickly intercomparison. Is there any other formic acid measurements out there?
Yes, there are several formic acid measurements at the site. So there were a lot of mass spectrometers at the SOAS ground site, and several of them also measured gas-phase formic acid. So we compared against the Wenberg group CF3O- SIMS, which I think is a very robust measurement, and that seems to be compared quite well. And I believe the PTR as well, which measures formic acid.
So you did compare to the PTR?
My students did that last week. Well, once again, I went on vacation. And so I have verbally been told that the intercomparisons look good, but I don't know exactly how good that means. But I know that the Wenberg SIMS at least compares well.
And I also know that they ran the PTRMS or in H0+, NO+, and O2+ mode.
Yes.
Do you have these defect plots also for that instrument?
Not yet, but from the CalTech FIXCIT data, Pavel Mistal ran the same set of reagent ions. So that data is apparently on its way to us to get processed to be put on the mass defect plots. And I'm pretty excited to see what that shows.
Any other questions?
Hi, yeah, I'm just curious if you considered the potential for entrainment of species emitted the day before that were mixed up and then left aloft that might be entrained during the morning, and then that as the boundary layer shuts down that afternoon, being that loss of that source that you would have otherwise maybe had during the morning phase.
So I think, and you'll have to correct me if I'm wrong, that if they would require a massive amount of entrainment that would be consistent every single day in order to do that. And from a meteorological perspective, I don't know if that's reasonable. And so I've thought about entrainment actually as a source in the morning, but the peak is to, we'd expect to see that a little earlier in the day, I think, than when we see the rise. But in terms of a fall for entrainment to be a sink, I actually don't really know. So I'll come and talk to you about that afterwards. Interesting idea.
I was going to ask if you know if there's a nitrate interference ever, and then you showed that there was the time period where nitric and formic didn't agree for somewhere other than SOAS, so maybe that's not important, but do you know if you have nitrate
If there's a nitrate interference,
at all?
we're very sure there isn't a nitrate. So one thing I should note is that, and I just realized it's in my acknowledgements, not in the data, the nitric acid measurements were not, we didn't completely trust our SIMS because of our inlet for them. So we used nitric acid from Kirsten Baumann at ARA. So no interference as far as I know.
Okay. Right, well, also if it agrees so well with all the other measurements.
Yes.
That's good too.
Yeah.
Okay, any others? Okay, let's thank Delphine one more time.
All right.